gusta decir que José Manuel conoce esta broma mía, que darle un micrófono a un cubano es peligroso. Nosotros le dimos el micrófono a Fidel Castro en 1959 y estuvo hablando casi 60 años. Entonces, imagínense darle un micrófono a un cubano, es peligroso. Yo solamente, casi no se oye, yo solamente me voy a referir a ello, me referí a los resultados del profesor Stevens, los resultados académicos. Pero también aquí hay algo que debe resaltarse. Él es de formación ingeniero y trabaja en un departamento de química aplicada. Además de sus asombrosos y copiosos resultados académicos, la cosa se puede, su actividad generando química aplicada, se puede resumir de esta manera, y ya termino. Tiene más de 20 patentes concedidas. Eso habla que la química que él está produciendo, además de ser química básica, investigación básica, además produce aplicaciones directas. Y eso es una de las cosas que es importante, resolver problemas. Una persona que ha producido más de 20 patentes, exactamente 23, eso indica lo que ha estado haciendo el profesor. Él nos va a hablar hoy de la química del fósforo y ya no le quito más tiempo. Chris, again, it is a pleasure to have you here, and again, the floor is yours.
Thank you very much, Professor Iglesias. Thanks a lot for having me here at Mexico City, my first trip to Mexico City. I'm enjoying it a lot, and the hospitality, especially from Martin as a friend, is very nice to be here. So today I will talk about some phosphorus chemistry we have been doing over the years in our laboratory at Ghent University, and I preferred to talk about different things. I don't like to go in all the tiny details of every subject, but I think especially for phosphorus, it's nice to show what are the opportunities, what are the different things we can do with developing some chemistry of phosphorus. And first, I will talk about our long story on addition of phosphites to azo heterocycles, and I will try to explain why we got interested for that. And then I will talk about three other things: synthesis of pyrabactin analogs, which have some bioactivity. Then I will talk of some very recent results on psilocybin. This is a new topic we are tackling, and we're just in the beginning. We have still lots of work to do there. And then I will end up with an application which is really very industrial based, but I think it's nice also to show what phosphorus chemistry can mean for industry. So first of all, why is phosphorus an interesting compound to work with? And one of the major applications of phosphorus chemistry is in the field of the flame retardants. As you know, a lot of brominated compounds are being used, polybrominated ethers and so on, as a flame retardant for a number of applications, wood, textile, and so forth. But the brominated compounds are under a lot of pressure because of toxicological reasons. So now a lot of people are looking at phosphorus as a compound to introduce flame retardant properties. But we are more interested in biological activity. And here, as you know, you have the amino acid, and the alpha aminophosphonic acid is, of course, the phosphonic analog of an amino acid. And because of that, because this alpha aminophosphonic acid can act as a transition state analog during the hydrolysis of oligopeptides. So therefore, these alpha aminophosphonic acids in a number of applications are enzyme inhibitors. An amino acid can bind to receptor, but this is on and off. with an aminophosphonic acid, it binds most of the time irreversibly and it blocks the enzyme. And therefore, a number of alpha aminophosphonic acids do have biological activities, such as aliphospholin is an antibacterial, here an analog of a homotyrosine inhibitor. We have a plant growth regulator, herbicidal activity, and as you see, these are very easy kind of compounds. Yeah, small molecules, but with an important activity. Here, a number of other very well-known antimalarial compound. This is not alpha aminophosphonic, but gamma aminophosphonic acid. Some antiviral compounds, some bisphosphonic acids, very important class of compounds as anti-osteoporosis. Glyphosate, the well-known herbicide, which of course is under pressure as well today. And then some glutamine agonist. So you see this alpha amino, beta amino, gamma aminophosphonic acids seem to be very interesting. And as I said, the bisphosphonic acids are also a very important moiety because they are the non-hydrolyzable form of pyrophosphate, which plays a very important role in our bones. So especially women, when they get older, you get some osteoporosis, and therefore these bisphosphonic acids are being used also to treat Paget's disease, which is a misformation, it's a problem with the bone formation and the bone degradation at the same time. So just to illustrate that the phosphonic acids, aminophosphonic acids, are an interesting class of compounds. So we got interested in that, and so we decided, let's look at aminophosphonates, but derived from heterocycles, not the acyclic, but the cyclic compounds. And so if you want to make a phosphorylated or a phosphorylated cyclic compound, you can start from your cyclic derivative and add the phosphorus derivative, or you can think about making an acyclic phosphonate and then later on trying to cyclize it in one way to get the cyclic compound. So for us, traditionally in our laboratory, we did a lot of imine work, imine chemistry. So it was obvious to us, start with an imine, add a phosphorus nucleophile, and then try to cyclize the compound. So that was our initially the idea to start. And so when you think about phosphorus nucleophiles, this is an easy way to look at it. You start from a dialkyl phosphide. This is a pentavalent derivative, and this is in equilibrium with the trivalent derivative, but the equilibrium is completely to that side. So a way to really force the reagent in a nucleophile with a free electron pair is to silylate the oxygen, and then of course you have a very good phosphorus nucleophile, and this is work described by Afarenkia and Charles Rees years ago in 1990. So we thought this is a good way. We have a very nucleophilic phosphorus atom, and then we add this to an imine. And so we looked at the work of Afarenkia, and they were describing this method. So we wanted to have gram quantities of a aminophosphonate, and then of course the idea was to functionalize later on the double bond and then do the ring closure. That was our initial idea. We did this reaction. We started from a very straightforward imine, and we introduced the trimethylsilyl diethyl phosphide, the one I showed you on the previous slide, and indeed you get this compound. And we followed the reaction, and the PhD student working on this, it worked, but there was a problem. We got, even after a very short reaction time, we had a derivative which we didn't know, what it was. It was a side product, and it took us quite a while to find out what it was. And it was this compound where you had introduced 2 phosphorus atoms, one on a type of Michael addition type of reaction, and then the addition to the imine function. So we got intrigued by that because this was not described at the time. To, in one reaction, get a dephosphorylation. And then we start looking, and indeed, if you keep going and you put 2 equivalents, this becomes really the major type of compound. So now we got more interest in the side product than in our initial idea. And just because I know Martin loves NMR, I just put also a slide on NMR, phosphorus NMR, to show you that we got 2 diastereoisomers, one where you see the coupling between the 2 phosphorus atoms and the other diastereoisomer. It's a bit broadened, but you don't see the coupling. So you get a diastereomeric mixture of the diphosphono compounds. Then we start looking at the mechanism. And it proved to be quite more difficult than we anticipated. So we did a complete study of the reaction mechanism and what happens. I will not go through all the details, but what happens is that this reaction works only when you have an acid in the medium. Yeah. And so here, the acid will protonate the imine, you get the iminium ion, and the first thing that happens is a 1,2 addition. But this 1,2 addition is reversible. And so it goes back and forth, but one time you get the 1,4 addition, then the reaction goes further by a 1,2 addition, and this 1,2, the second 1,2 addition is not reversible anymore, and so finally you get this bisphosphorylated product and we published this whole story on the mechanism in Angewandte long time ago. But this story is still going on today. So later on, we said, what would happen when we have an additional double bond? Would we get 1,6 addition together with 1,4 addition, together with 1,2 addition? What's happening? And it became even more complicated. And as you see, we published this later on. This is already 2017 to figure out the whole mechanism. And what happens again is that you get first the 1,2 addition, again a reversible addition, and then you have mostly 1,4 addition, but also a little bit of 1,6 addition. And so finally, you get mostly the bisphosphorylated compound with a remaining double bond, or you get the 1,6 addition and then also the 1,2 addition. So in this way, we got this is a one-pot reaction. So a one-pot reaction that gives you immediately the bisphosphorylated compounds, and we were then intrigued, how far can we go? Is this a general reaction or not? And so we thought, well, we were looking at alpha-beta unsaturated imines. What would happen if this alpha-beta unsaturated imine is part of a heterocycle? And so the most easy compound would be a quinoline. So here you have your alpha-beta unsaturated system. You treat it with the silylated phosphite, the dialkyl phosphite, and we were surprised you indeed get this compound. So the reaction is that fast that you break up the aromatic stabilization. So we thought, well, this is aromatic, this is very stable, probably the addition will not work. It does work. And again, you get one reversible 1,2 addition, 1,4 addition, followed by 1,2 addition to get these kind of compounds. And this is interesting because, as you know, in the pharmaceutical industry, they try to escape what they call escape from flatland. So they want to have not always flat molecules, but molecules with a 3D structure. So here we start from flat land, the flat molecule, and here we have a molecule with a 3D structure. We could even go a step further. What about phenanthralenes? You have the 110, the 17, the 47 type of phenanthralenes, and also here the same type of reaction is working. You introduce in a 1,4, 1,2 manner the 2 phosphorus compounds in all the compounds. You might ask, why doesn't it happen a second time? Why don't you get a second reaction there? Well, the reason is simple. You have to activate the nitrogen with a proton. And of course, if you look here, the most basic nitrogen is this one. So if you protonate the nitrogen, it will always be this one and never this one. So the reaction stops after one round of reactivity. So you cannot get, or you cannot introduce 4 phosphonate groups, it stops at 2. So that was kind of clear, and you see in some kinds the conversion is low and the yield is low, but still you can get these type of compounds. And then we wanted to see, what about the pyridine? It would be very interesting if we could do this reaction also on pyridines. And a number of people in the group have been tackling this problem, and still today we are struggling with that. Pyridine is a very difficult one to phosphonylate. And the only example we found in the literature is of one of my friends, Roberto Lavilla from Barcelona, and he published this. He started from a pyridinium salt, and he was able to introduce 2 phosphorus groups in alpha, and then finally he went to the 1,4-dihydropyridine. And we spent months on this, trying to figure out what was going on. So finally we got some results now, but as said, we are not there yet. And it seems to be a very, very difficult reaction, and it all is connected to the details. So first of all, the pyridine we know now needs to be extremely dry. A proton to activate the nitrogen group doesn't work, so now we use the benzyl group. We have a benzyl pyridinium salt, and then it works. And also the benzyl bromide that we use to make this has to be washed with sulfuric acid and distilled. If there is a slight impurity in the benzyl bromide, reaction doesn't work, and we have to evaporate carefully the benzyl bromide. So it's not the most convenient reaction, but still we are there. And what is now surprising, this is the first time that now we can introduce 3 phosphonate groups on a pyridine going to a triphosphonopyridine. And here, and this is thanks to the work of Lavilla, Professor Lavilla, this 1% of silica that you need to add to the reaction is crucial. It seems to play kind of Lewis acidic type of medium in order to get the reaction to work. So now we get this type of compounds, and we are collaborating with the Free University of Brussels. These type of compounds seem now to be interesting, and they do have some flame retardant properties. So we're still trying to work on this and get some reactions to work. As you see, it took us a long time to get some decent results here, but now if you really heat it up for 100 degrees, you get 95%, but still we are having trouble to really know what is the orientation of the group, which diastereoisomer do we get. Also, it seems that the diastereomeric ratio is changing during purification, so we really have to look carefully into that. So also, when you put here a methyl group on the pyridine, the reaction gives the 1,2,1,4 addition, but you see the yield is very, very low. And of course, we want to see if we could get further there. Here, just to show you that depending on the type of purification we are using, you get like different results. Also there's still some work to do to know what's going on. Apparently on the column, the diastereoisomers are rearranging probably, so we still have to look at this. And here we have also another way to do it, and we can either use the silylated dialkyl phosphite, or we can use the triethyl phosphite in the presence of formic acid, and then we get also these type of compounds. Of course, we wanted to also get some feel for the mechanism. Does it go again through a first 1,4 addition and then 1,2 addition? And here we can prove that probably it is like that. When we take the molecule with the methyl group on the 4 position, you block the 4 position, and then the reaction doesn't work. We get no compound, nothing can be formed. So we suppose that the reaction again goes through first 1,4 addition followed by 1,2 addition. That was where we are now on our story with on the story with the diphosphonylation. Let's shift gear and look at some other interesting compounds. Well, this is a plant hormone, abscisic acid, which has a number of functions in plants, the ripening and so on and so on, seed germination. And a few years ago, this compound has been described in a professor from Davis who found that this molecule, pyrobactin, has the same kind of function as ABA. Yeah? So quite important, this pyrobactin molecule protects against drought. And of course, in our world with climate change, with drier conditions, that seems to be quite interesting from an industrial point of view. Could we develop a compound, if we spray it on a plant, that the plant can survive with less water? So that's the idea we had. Can we develop something in order to protect plants against drought? This compound you cannot use, ABA. It's very unstable. It's hard to make. It's too expensive. So this one is out, the natural compound. And when I read the first time about this pyrobactin, the author had patented the compound, but he writes in his own article that he does not think that this compound will make it to the market, but he doesn't say why. And that triggered my attention. What is he saying? When you publish your work and it works on a plant, and you say in your first publication, I don't think it will work. So we started thinking, what could be the problem? And maybe it was naive. We thought, like, this is a sulfonamide. If this is an aqueous medium and this would hydrolyze, you end up with an amine and a sulfuric acid derivative. Of course, you could think that the sulfuric acid derivative would be very toxic for plants. It's too acidic. So we thought, well, why don't we try to make the phosphorus derivative? If you have a phosphonamide and it hydrolyzes as well, plants are very well suited to deal with phosphonic acids. Yeah? Because DNA, RNA, a lot of phosphoric acid derivatives are present in plants. So we set off with the idea, let's try to make the phosphorus analog of pyrobactin and see where we get. So I don't want to go into the detail why ABA and this pyrobactin works against drought, but ABA is binding the ABA receptor. This inhibits, again, another family of proteins, PP2C, and so that prevents this reaction here, and that leads in a second stage to the activation of what are called stress-tolerant genes. And if you don't have this binding, you block this and that the plant dies. It's a very complicated biological system. There are numerous publications on how ABA is working, how pyrrobactin is working, and it works through a cascade of inhibiting certain proteins, and then finally these stress-tolerant genes are either activated or not activated. But this is really biology. We got more, what's going on? We got more interested in the phosphorus analog and to see what was going on. And as said, a cell knows very well how to deal with phosphorus compounds, and these are not lethal to the plant. So we designed a synthetic pathway to deal with that. We started from brominated naphthalene or another aromatic compound. Then we first did the Hirao type phosphorylation with palladium, or we could do it with the palladium and a phosphide, or first we can do a lithium exchange with the bromine and then react this with a chlorophosphoridate to get the corresponding phosphonate. And then the most difficult step was the selective hydrolysis to get off one ethoxy group to have the hydroxy derivative, and then you activate this with thionyl chloride to get the corresponding phosphorate chloride, and then you can react it with a number of different heterocyclic compounds to get this family of compounds. We did this for a whole family of different compounds. As you see, we introduced the same group as in pyrobactin, but also the phenyl ring, having compounds with the nitrogen on another position, having the bromine on another position. So we made the whole family of pyrobactin compounds. And to our surprise, this kind of idea of changing the sulfur to a phosphorus, it works. Yeah? We have seen that we looked at closing the stomata of plant leaves, and if you treat the plant leaf with these compounds, the plant leaf really shrinks and closes the stomata. So by doing this, the plant is not evaporating water through the stomata, and so it can survive with less water. So this compound is the natural compound, ABA. The plant hormone is still doing this better, but you can't apply it in practice. But some of our compounds work very well, and this was even better than pyrobactin. Pyrobactin is the yellow here, which was described, and we could do it way better. And we're now working with a company to see where we get when we can treat plants with these type of compounds. There was only one which is doing just the opposite. This compound is opening up the stomata, and so also companies are interested because this could serve as a kind of herbicide. You treat the plant, it opens up, it loses all its water, and it will die. So very strange. One compound, which is very similar, opens up the stomata, the other one closes it. So we're looking further into that. And also, one of the activities of ABA is seed germination. So if you treat seeds with abscisic acid, it starts germinating. Most of the compounds that we produced didn't do the job. There was only one compound which suppressed the seed germination with 60%, which was way better than pyrobactin itself and ABA. So this inhibition of seed germination is also of importance for agricultural applications. If you store grains somewhere to use as food, you don't want that these seeds are starting to germinate when you store them. So also here, there might be some application. Let's now go to another. I told you that I would briefly touch on 4 different aspects of phosphorus chemistry. And this is the most recent one we are working on. And this is on this type of molecule, and this is called psilocybin. Psilocybin is a natural compound that you can find in mushrooms, in psilocybe mushrooms, and it works against the 5-hydroxytryptamine receptor. So it is used from ancient times to have hallucinations. So if you eat the mushroom, you start hallucinating. And this is kind of important because it says that this compound is passing the blood-brain barrier. So it has the ability to go to the brain and to do something. And so this compound, a lot of work has been done on this compound. And now, since a couple of years, they have seen that it has also some very interesting activity against depression. You might know if people have a depression and you need to take antidepressive drugs, most of the time they start only working after 4 to 6 weeks. And of course, if you're really depressed and you have some suicide feelings, it can be too late. Yeah. So a lot of activity goes to drugs that could work much faster. And this compound seems to be one that is working after a few days. So that's why a lot of interest is in this psilocybin, but of course you don't want to have the hallucinating properties. So we thought, what can we do? It's a phosphorylated compound, so we got interest in that. And it's not the only compound. You have some very related compounds. Aeruginacin, this one here, bufotenin and bufotenidine, and they all have different activities, but more or less in the same area. One has some euphoric experiences. The other one is psychoactive, and some bufotenidine leads even to temporary paralysis. So it means it really acts as a very strong biological active compound. So what would be the idea? So first of all, how does it work? Well, it is well known in the literature that it's not psilocybin that is doing a job in the brain, but it gets hydrolyzed to psilocin, and it is this compound which is active. And you see that this is very related to serotonin, which is a neurotransmitter, so it has some similarity with serotonin. But it is known that you need the hydrolysis. And this is done in the passing in the liver, and then it goes to the brain. So we wanted really to do something different because everybody is looking at this hydrolysis, and we thought, let's do something completely different. So what we are now after is to leave out the oxygen and have the phosphorus directly connected to the aromatic compound. We don't know what it will do. Probably it will not be psychoactive, but it might be an inhibitor of the enzyme which does this hydrolysis. So that's the idea. We don't know yet where we are, but we are after this. So that's the retrosynthetic scheme. We will first, from the phosphoric acid, we will first go through the ester. This side chain is described in the literature that it can go through the diketo compound. We can introduce the side chain on the nucleophilic position of the indole ring, and the phosphonate could come from the bromine. And so this bromoindole can come from this brominated nitrobenzene. So we started off about 2 years ago. We thought we would be much faster in developing this chemistry, but we got some surprises. So this is a described reaction. You start from a brominated nitrophenyl compound, which you treat with the dimethyl acetal of dimethyl formamide. You deprotonate, and it reacts with this intermediate to introduce the side chain, loses methanol, so you get this unsaturated amine, which you can then take and reduce the nitro compound with zinc and acetic acid, and it ring closes to the bromo indole and 60%. After some work, we were able to reproduce that. It's called the Lime-Gruber-Baccio indole synthesis, and this works. But then came the real trouble trying to introduce the side chain. That was working quite well. You can treat this with oxalyl chloride in an ice bath. You get the corresponding addition product, and immediately you react this with dimethylamine to get this compound. And here we are, but then it failed. Yeah, we tried almost every reducing agent that we have in the lab, but here we're stuck for the moment. We are not able to reduce this compound. Although it has been described in the literature, we are not able to reproduce this. So we thought, well, let's change the synthetic methodology. Here we have the bromine. Maybe we have a problem with the reduction of the bromine. So let's first replace the bromine with phosphonate group and try then the same type of methodology. So just switching the number, order of the steps. So here we started from the bromo indole, and then we wanted to do the Hirao type coupling with palladium acetate and a phosphite, but this fails. We don't understand, but this is a very difficult step. We don't get to this compound very easily. And it was kind of by accident, because another PhD student in the group was working on NHC compounds and heterocyclic carbines, that we used one of the palladium derivatives with this very specific N-heterocyclic carbene, that we were able finally to get 32% of this phosphorylated indole. Also there, we still need to improve this reaction. And so now we are here. We can have this compound here. This works. But again, now we're working to see if this group, if we can reduce the side chain in order to have our phosphorus analog of psilocybin. So this is work going on in the group for the moment. But just a few words on this one, because this is a very interesting field on continuous flow chemistry I was talking about yesterday. And one of our colleagues in the Faculty of Sciences is Steve Noland. He's very well known on N-heterocyclic carbines. He's one of the big guys in this area. And he is producing a lot of organometallic compounds with N-heterocyclic carbines. And we started 2 years ago to try to translate this kind of methodology to a flow synthesis. And now we have a very easy way. You simply take the imidazolium salt, you mix it with palladium precursor, and you simply pump it over a potassium carbonate bed, solid bed of potassium carbonate, and you get immediately the synthesis of the palladium N-heterocyclic carbene. So you might know that these N-heterocyclic carbenes are normally made from an imidazolium salt, treating this with a strong base in order to make the free carbene, and then condense it with a with your metal. But this is quite unstable, so people have been trying to modify it by transmetallation. So first make a salt and then do a transmetallation. This is a possibility. And recently, the group of Steve Nolan developed another methodology where they can start with the imidazolium salt and treat it with a weak base now to make the same thing. And now we were able to translate this kind of methodology in flow, and you can make as much as you want, whereas if you do this route, that you are very limited in the amount of compound you can make. And so this seems to be a very general method. And recently we published a series of publications on this issue. You could simply take the imidazolium salt, you mix it with your metal precursor, and you get to the methylated compound, and this one is now kind of the precursor. You can have the copper, you can have the gold, you can have palladium. We're working on platinum, and this is the precursor to introduce alkynes, to introduce sulfides, to introduce carbozols, and even to make linear gold derivatives. So that seems now to be a very nice precursor to do a lot of work, and we're still working together with Steve Nolan to develop this methodology, and the aim is that we would probably next year try to create a spin-off to get this type of chemistry working, and also try to provide it to the community. It also works with selenium, it works with sulfur, so we are there on a very nice route to make all these kinds of derivatives with anhydrocyclic carbenes. Let's come to the last point of my lecture of today, and this is something completely else. And I stumbled into this area. I didn't know anything to start with, and probably that has been my luck. Sometimes you're lucky not to know a lot of a certain area, because then you try things that other people think that would not work. So sometimes it's not an advice to the young people, but sometimes you're lucky if you don't know a lot of a certain area. And so one guy who is working in the harbor of Antwerp, he's working for BASF, big company, huge company, 5,000 people are working there. And he came to me with the question, when I ride to my work in the morning, I feel the heat coming towards me when I approach the company. They have a lot of big industrial processes at 600 degrees, 400 degrees, and a lot of heat goes out and is wasted. So, of course, the idea, if you can recuperate waste heat, that would be very nice in view of reduction of CO2 emission. When we looked in the literature in Europe, they estimate that about 180 gigawatt is lost of heat, which is between 80 and 150 degrees. If you go higher, there are methods to use that, but in this range, nothing was there. So we wanted to find out. He came to me, do you have an idea to come up with a solution? I had no idea. So once in a while, we went out for dinner to talk about this idea, and he was thinking about enzymes and so on and so on. I said, no, 80 to 150 degrees, this cannot work. Enzymes are not the solution. We need something else, but I have no idea. And then I thought, well, what is nature doing to store energy? Most of the time, nature has been evolving over millions of years. Most of the time, there are some good solutions in nature. So what is nature doing? It's using ATP and ADP. So what does it do? It shuttles phosphate between two molecules. You have the energy-rich ATP. It hydrolyzes. It gives you phosphoric acid and ATP, and that is a cyclic process. But of course, to use ATP and ADP on an industrial scale, this is not going to work. So I started thinking, can we find a very simple mimic of this kind of process? So the most simple mimic is a phosphoric acid. So the first thing I did, and I didn't want to tell anyone because I thought maybe it's a very silly idea, so I bought polyphosphoric acid. You can buy this. And I thought, if you hydrolyze, if you put water and polyphosphoric acid, and it doesn't become very hot, my idea is nothing. So I did this, and indeed, if you hydrolyze polyphosphoric acid, you have to be careful because it becomes very hot. So I thought, well, I might have an idea. Why don't we try to take a phosphoric acid and try to use the waste heat between 120 and 150 degrees and try to do a kind of polymerization of phosphoric acid. As happens here, ATP, ADP. And so I did. You heat this for a time, and you get a solution, a mixture of things, but it didn't matter. And if you then put water again, the temperature rises to 230 degrees. And this works with a yield of 50%. So simply taking a phosphoric acid solution, you heat it, and then later on we saw that it's much more complicated. What happens is that when you heat a phosphoric acid solution, first of all you start evaporating the water, so the phosphorus content starts rising, and then at a certain moment you get formation of some oligomers. It's not a polymerization, it's just a few oligomers. But then when you put water, it's mostly the dissolution energy together with the hydrolysis that really kicks up the temperature. And so by doing this, the temperature rises with about 90 degrees, and you can do this with a yield of 50%. So what happens is you take the heat at 120 degrees, you heat your solution, so you start removing the water, the phosphorus content is going up. At a certain moment, you stop and you add water, and then you release a lot of energy, and actually what you did is making a chemical heat pump. And so that's what we found and what we now were doing. This was a very simple setup in the lab. We took a patent on the idea, and the guy who initially came to me, he quit his job in BASF. He started his own company, and that is now called QPinch. And today there are about 20 people working on developing this for an industrial situation. We took part in 2015 with the idea in the RSC of the Emerging Technologies competition, and we were lucky to win the first prize. There, this is Walter Duchesne from BASF. And so now he is building with the company this on an industrial scale. This was some very initial setup in the lab. This was built in Antwerp, in the harbor in Indaver, and this is now where we are today. It's a 2 megawatt plant to recuperate waste heat, and this is now built in Borealis. A lot of big petrochemical companies are now interested to build this system, to use this waste heat, put it up to a higher energy level, and then you can heat things, you can make steam again, and so that saves a lot of CO2 where you otherwise need to use gas to produce this heat. So by this I want to end my lecture. This is, we are 4 professors in our faculty on organic synthesis. We combine forces because we have to pay for all the equipment. So one group cannot really be sustainable to pay for the NMR, the GCMS. So we joined forces, and this is the whole group with my 3 other colleagues who did the work, thanks to them. And maybe for you who does not know where Belgium is, because Belgium is a tiny, tiny country here in Europe, across the channel with England, between France, Germany, and the Netherlands. And if you look at Belgium, Brussels is the capital, and Ghent is between Brussels and the seaside, so that's where we work. And so by this, I want you to try to convince you to come and come to Ghent, because Ghent is a quite nice city and has some very, this is the most well-known piece of art in our city. It's a painting from 1432 of the brothers van Eyck. It's a very wonderful painting who just got restored. So I think it's really worth coming to see this painting. These are some pictures of the center of the city. I also showed some yesterday. And by this, I want to thank you for your kind attention.
Well, thank you again, Professor Steven, for this interesting talk. We are open for questions. I don't know if we will have people following us in the internet. If it is the case, we will be collecting the question as we did yesterday, and on time Professor Steven will answer the question. But now we are open for question here. Professor,
thank you for your interesting talk. You mentioned that Pyridines are very reluctant to undergo phosphorylation.
Yes.
And is there, however, when you tried benzyl as in the nitrogen, you can obtain the compounds. Is there any particular reason for benzyl, or could be any other group? And my second question is, have you tried conditions similar to the to obtain research compounds like benzoyl chloride, because it should work pretty similar?
Can you repeat the second one?
For the preparation of the research compounds, you treat or you try pyridine or quinoline
Yes.
with benzoyl chloride, and you activate the heterocycle, and now add any nucleotide.
Yeah, well, to answer your first question, why the benzyl group, we tried some other ones, but benzyl seems to be the best one to work. We tried with methyl groups and some other alkyl groups. We don't understand why the benzyl is better, because you could think that you also could debenzylate in some cases, which could complicate the case. We are still working on this, but at the moment, and it can change, but at the moment, the benzyl pyridine is the best one to try to introduce the phosphorus groups. But I have to admit, don't try it yet, because it's a mess for the moment. It's not working properly. We are progressing, we're getting the compounds, they seem to be interesting, but we still need to work on the methodology, because also the workup is complicated. We lose a lot of compound during chromatography, so we're not there yet. And I don't understand, for quinoline, it works very nicely with the proton. For pyridine, it doesn't work at all. So I can't answer the first, well, completely the first question. For the second question, to introduce the benzoyl group on nitrogen and then look at it, we did it also for benzyl, for the quinoline, and it works, but it is, the yield is a bit lower than with the proton. We normally use sulfuric acid, and you need one equivalent of sulfuric acid, and that's of course very easy, and the yield is better. So to answer, yes, it works with benzyl group, but the yields are a bit lower.
Thank you very much.
You're welcome.
Another question? Claudio?
Gracias. Bueno, so my question, I have two questions. The first one is because we are not very familiar with the use, well, at least in some of the groups that I have been, of the use of phosphate, phosphoric acid, all the phosphoric chemistry derivatives. So in terms of toxicity, in terms of activity, so what we will expect working with those compounds with without
Well, phosphorus chemistry has, of course, not a very good image because a lot of nerve gases are of phosphorus compounds. If you have a phosphorus fluorine bond, then you have to really watch out because these are very, very toxic. Also, the phosphites themselves are not very healthy, so you have to be aware of this, like dialkyl phosphite and triethyl phosphite. These are very good nucleophiles, so they react with electrophiles in the body, so they're quite toxic, but the phosphonic acids are in a complete other ballpark. They are not toxic. Well, everything is toxic, but it depends on the concentration. So it seems that for a lot of biomedical, medical applications, the aminophosphonic acids are not a problem. Think about amino bisphosphonic acids to treat osteoporosis. These compounds are on the market. The glyphosate, which is now under a lot of discussion, the Roundup, which we use as a herbicide, and still there's a lot of discussion if it's really the glyphosate which is toxic or the combination of glyphosate with a tensioactive compound which is in the formulation. And apparently in the literature there's still a lot of debate about this. Is this now only about the active compound, or is it the toxicity of the active compound together with the surfactant which is in the formulation? And of course, like always, there are people saying this one, there are people saying this one, and of course politicians, they decide, well, if it's not clear, let's be on the safe side, let's try to stop it. But to me it looks like, you know, if it hydrolyzes, you get 2 amino acids which should be fine.
Yes, thank you. So a follow on that. So you discovered, you obtained 2 compounds where one is performed similarly to the commercial compound, and the other one is the opposite, as you mentioned.
Yes.
Would be serving one purpose, and the other similar to what Monsanto did. So in that regard, it would be, I don't know if you're in liberty to say, it would be good to know what the structural differences are for such a marked activity, right?
Actually, what I think is that they interact with another receptor. So, of course, we always think when you have a library of compounds that are very similar, you kind of immediately think that they interact all with the same receptor. But maybe this is not true. Maybe the ones that closes the stomata work on a certain receptor, and the other one which opens the stomata could react with another receptor. So I think it is something like that. But of course, I'm a chemist, I'm making molecules. I'm very interested what it would do, but yeah, we are not equipped in the lab to really look at these details, what's really happening in the plants. We're working together with a company who is spraying the plants and see what's going on, and also about ecotoxicity, which is also a very important issue when you want to spray something on the field. What's the effect on ecotoxicity and so on? So we're a long way to a real application, but at least it's intriguing to see that we can interact with certain receptors. And the idea, I think, is nice. If you could, because the plant opens the stomata just to take CO2 from the air and do photosynthesis. But when it stays open too long, it loses a lot of water and it almost kills itself. So if you could regulate, you know, that it closes a little bit. And a second issue that we have to think, if you spray it, you need to be able to extend that for a certain period. When they close the stomata for 1 hour, you didn't win anything. It should be for a long time, and the idea would be that you only treat plants when you know that there would be a very dry period. So more and more in agriculture, you try to prevent to use a lot of chemicals, yeah, which is okay, which is, I think, the idea of sustainability. So this kind of, the idea is to use this kind of compounds only when you know in advance, like the following 2 weeks will be very hot and very dry, then you spray it, you have it for a certain while, and then afterward, yeah, it degrades and you have no problem with toxicity. But of course, this is theoretical. We're a long way off from an application, but then again, I showed you that sometimes a very straightforward idea can lead to a real industrial application.
Thank you very much.
Okay, more questions? Well, again, to the person who are following us on the internet, please send the question, and they will be collected, and Professor Stevens will answer the question by email. I have a couple of questions. Could you please show us slide 13, the one with the dephosphorylation of quinol?
Slide 13, yep, this one.
It may sound a little bit naive, but anyway, I want to make a question. You perform a first phosphorylation, and then you define the plane, and you will, the next one, the second, it is cis or trans? Because you have two possibilities.
Yeah, the major one is the trans. The major one is the trans, and the minor one is the cis.
But it could be interesting to try to isomerize these to have the cis. And have you tried this by adding, let's say, some acid to protonate the oxygen, and then to get something like enol into.
You're touching a very sensitive point there. I tried a lot, and it didn't work at all. We spent a lot of time doing this, trying to do it the same with the oxygen type of compounds. It doesn't work.
And possibility could be use sodium methoxide to subtract this proton here, to subtract the proton. Then the living group, you won't have the hydrolysis, the substitution, because the living group.
I don't think this proton is not very acidic. I don't think you will be able to take it away. We didn't try. What we did try, and this is work that Marta will be maybe working on today, because that's one of the things we want to do, what we want to do is to use a chiral acid to protonate the nitrogen. If you protonate the nitrogen with the chiral acid, for example, camphor sulfonic acid, we hope we could get some diastereoselectivity, enantioselectivity, but on the other hand, I have been very reluctant to start this because we know that the first thing which happens is the 1,4 addition. So if you protonate the nitrogen, your chiral inductor will be too far away. But people are asking me the question, and I think it's a relevant question, but I don't think it will give a lot of enantioselective induction, because we know that first step is 1,4 addition. So if we have a chiral group kind of hanging on here, probably the induction will be too low. But we will do it. We will try it, but I'm not expecting a big result. But still, who knows?
Well, my second one, did you show us slide 14? 40.
Oh, 40.
This one. You know, one of the things that we have been doing is laser type cooking.
Yeah.
Alkaline. And one of the first steps was laser and Eglinton with this more or less related, is dimerization of alkyne. But when it comes to cross-coupling, it is risky and it is complicated. And one of the things that is done is that to activate one of the alkynes by methylation. In fact, one of the first step in bond coupling is methylation.
Yeah.
And then the second attack of the alkyne.
Mostly with copper, right? In glazer?
In glazer is copper.
Yeah.
In copper. I show you that contribution that we use palladium to
Mhm.
the same. My question is, have you ever read this compound as a precursor for the
I know where you're going. No, we did not. To have this as a precursor for type of glazer type couplings?
yes, cross-coupling?
Cross-coupling. Of course, this is, well, Steve Nolan is really the expert in this kind of chemistry. I cannot talk for him if he never tried it, but I'm not aware of it. We didn't try it for sure, but I'm not sure if Steve tried it, but I can ask him. But he has been very active in the field. He might have tried it, but I'm not sure. I can't answer the question.
Okay, well,
It's a good suggestion to look at it, yeah.
well,
Yeah.
any more questions? Okay, let's thanks again Professor Steven for being here and for the two interesting talk. Let's thank you.
Thank you very much.
Thank you.
You're welcome.